So I plan to go through notebooks 7A and 8. That is the LSUV and the data block. And then next time to go through the the optimizers part. I think that's all that's in chapter 11. I'm not sure. But I'm, as usual, we're probably not going to make it through what I wanted to. 07A is the LSUV notebook. He covers that in about 3 or 4 minutes in the lecture. And then for the next hour or so, he goes through the data block API. So I'd hoped to get through that today. All right, let's see, slide sorter. But I had some questions from last time, and I posted something on the forum. So let me see if I can take you to that. Got to change the focus here. My batch norm. Okay, can everybody see this? This is a forum post about running batch norm in lesson 10.
Yep.
Okay, so you'll remember from last time we went through this running batch norm algorithm, and so I went through it again, and even though we discussed it at the end of the meeting last time, but I went through again and I had a bunch of questions about it. And I wrote down the questions and submitted them to the forum, hoping somebody would answer the questions. But instead, they didn't answer the questions. My main question is really, so some of the questions are just minor, like here's question 1, shouldn't self.mults and self.adds have the size of the input batch, which I think that it should. I think the reason why it works is that the reason why these dimensions work is because of broadcasting. So it happens that automatically that it expands it to the right size. But I have to try some experiments to make sure of that. Another minor question I had was they did this detach operation to the sums and squares buffers. And my question was, why don't they also do it for the batch count and step buffers, actually? So let's go back to the top here. This is where they do. Okay, so I put in a lot of comments here because I tried to understand this for myself, and maybe these comments will help you to understand everything too, if you haven't. So at the top, he does the initialize with this superclass. He brings in these constants, MOM, which is for momentum, and EPS for epsilon. He brings those constants in, and he sets them here. Then he adds these scale and offset parameters to the model. So this is how you declare parameters, and that means that so mults is a parameter now. It's the scale factor, and adds is the offset. And I think they've maybe changed them in the later versions. But the point is that this is how you set a parameter to be tracked by the model to be actually solved by the model, which means that it's going to be solved by backpropagation. Okay, so that's this set of initializations. But then he has a set of register buffer commands, and what that does is it adds what they call a persistent buffer to the module, which means that you're sticking this parameter onto a place where it can persist from one call to the next. In other words, it remembers the value that it had from the last call. So he's defining these new variables: sum, squares, batch, count, step, and debias. And my question was, he does this detach operation for sums and squares, and that means, I guess that speeds it up, because detach means that it detaches from what they call the computation graph, which means that it no longer has to keep track of the gradients. Okay, so that's a convenience to maybe speed things up. And I was wondering why he didn't do it also for the other buffers that, the other variables that were initialized in that register buffer command. So these are trivial questions, but the main question, okay, so.
Just to add a note there, Joseph, I think stuff which is in the register buffer are not parameters.
That's right. That's right. Exactly. Those are not the same. They're not on the same footing as the parameters.
So you're not tracking the gradients for those.
Yeah, that's another thing. I mean, I don't know why it's necessary to do that detach command, because as you said, it knows that it's not keeping track of the gradients. But in any case, it just seems logical that if he's going to do it for these first two, he should do it for the rest. In other words, detach the rest of them as well, right? So those are sort of trivial questions. But really my main question was, wait, maybe we should go through some of the rest of this to get here. I was just commenting on this DIMS, remembering that that X, which is the batch, is a 4-dimensional tensor, and the 0 dimension refers to the sample number in the batch. The 1 dimension refers to the channel number, and the 2 and 3 dimension are the weights matrix, the X and Y, the sort of the row and column of the weights matrix, right? So when he sets these dimensions and then he takes the mean over those dimensions, what he's doing is he's getting a per channel mean, so that the output size, because the keep dim equals true command, it keeps the size of it keeps the original tensor size. So what happens when you average over the dimensions 0, 2, and 3 is that you simply get you get a new tensor that has the same size as the old tensor, except that it's a per channel mean. So this NF is the number of channels. So there are 3 numbers in there. The mean for the first channel, the mean for the second channel, and the mean for the third channel. So actually, NF isn't just 3. In the final output it's 3, but I think in intermediate outputs it doesn't have to be 3. So let's see. So what is he doing here? He's keeping the sum in. He's keeping the sum and the squares. The sum of the weights, that is, in other words, he's summing over all the weights in each channel, right? So each one of these entries in NF is going to have the sum of the weights in it for S, and for SS, it's going to have the same size, but the entries in SS are the sum of the squares of the weights. That is the mean of the sum of the squares of the weights averaged over all of the averaged over all the other dimensions but the channel. So again, it's going to have one number for each of the channels. All right, so S and SS are keeping track of this, the sum of the weights and the sum of the squares of the weights averaged over everything but, well, how do we say this? Averaged over all the dimensions but the channel. Okay, I just made some notes about which we don't have to go over, but this is my main question here, is what's the logic behind this momentum formula? They introduced this formula without any explanation. As far as I could tell, I listened to the lecture several times, and they never give an explanation for what's behind this formula. So I played with it a little bit to see what it does, and if the initial momentum, which is usually defaulted, in this case it's defaulted at 0.1, and if the batch, for a small batch size, let's say the batch size is 2, then the momentum MOM1 by this formula is going to be 0.1, so that's fine. If the batch size is bigger, like 64, then MOM1 turns out to be 0.9. And so in general, MOM1 increases with batch size, and of course its maximum value is 1. So it's so all I can tell about MOM1 is that it lies somewhere between 0 and 1. But I'm not sure why they use this formula for it. Anyway, I had some other questions about it too, and I put this on the. I spent a lot of time because if you can formulate a question in a way that when you get the answer you'll know something, that it's worth it to spend time to formulate the question. So I asked, I think 7 questions altogether. No, 7 questions altogether, and just try to get some answers. But what Jeremy did was he basically threw it back at me and says, "These are interesting questions. Why don't you do some experiments and let us know what you find?" So, fair enough. Anyway, so let me get back to the presentation that I had. Any questions so far? Okay, back up here, next page. Then I noticed that in the lecture, Jeremy shows a simplified running batch norm, which is not the same. He's showing us a notebook that has the same name, the 07A _ LSUV notebook, but it's not the same as the notebook that we see in the repo that we get from cloning the repo. So there's something that he's done, that didn't. It's a dev version or something, and we don't have access to it. And he showed, okay, so my complaint was this batch norm algorithm is really convoluted and difficult to understand, and I asked for some explanation. But then I found out, listening to lecture 11, at the beginning of lecture 11, he shows us this simplified running batch norm thing where they've made it simpler. They've eliminated this debias part, which is really confusing. That was one of my other questions. And so it is smoothed out. The algorithm for running batch norm, simplified running batch norm, is somewhat simpler, but we don't have access to it. So I asked a question about that on the forum, and I still haven't got any answers, like where can we get this simplified, quote unquote, simplified running batch norm? I think I made a note somewhere where, well, I can just look at this comment really quick, like we did before. Let's see, I'll stop sharing.
Just simplified batch norm is right at the bottom of your previous notebook.
Right at the bottom of the previous notebook.
The 07 batch norm notebook.
Did I miss that? Let's see, 07 batch norm. Okay. Oh, 07 batch norm, sorry. Batch norm, that's fine. Oops, sorry. Okay, let me go to the original version, because just to make sure that I didn't mess things up. 07 batch norm, this is supposedly the original version from the repo. And oops, something. Instance norm, group norm, running batch norm. I don't see a simplified.
Yeah.
Yeah, this is.
I think you don't have the most recent version, or the version that I have and the old version you have are not the same.
Really? Because I did my update. I did a git pull from the repo just days ago.
Weird. I haven't actually done a git pull in a while, but mine seems to have it.
Interesting. Okay, well, let's see what happens if we went online and look for it. Go to the. Let me share my page, my screen with you. Let's see. Share screen, and I'm looking here. That's not what I want. Oh well, that's okay. Okay, are you seeing my screen? I'm in the forum. Oops, now I'm not in the forum. But I'm going to go to Fast.ai just to look at in the repo. let's see. GitHub. Okay, so we go to, oops, wrong place. Go to course 3, course V3, and then go to notebooks, and then go to DL2. Is my screen showing?
Yep.
What I'm doing? Yes? Okay, so I'm going to go to 07 batch norm, which is 3 months old, but that's the latest version. And if I go into it, I see there's batch norm. Running batch norm. Yeah, so where's the simplified running batch norm?
That's weird, it's not there.
Huh, so where are you getting yours from?
So I actually pulled mine before Jeremy combined DL1 and DL2 in the course V3. I don't know if something after he combined.
Okay, so something's, anyway, I asked a question about why isn't the latest version in the repo. Anyway, probably we should move on. I'm going to my next page, unshare, share again, there. Okay, whoops. Unshare, share the screen and share that. Share. Okay, back to my, is everybody seeing my PowerPoint slides? No?
Yep.
Oh, you are? Okay, great. Okay, next page. Simplified running batch norm. And then here's coming to this this notebook, which he covers in the first 3 or 4 minutes of lecture 11 of lesson 11. In the paper, all you need is a good init. That's the paper that he's going off of. He basically seized on this formula that are using. The concept is to layer by layer, go through the layers one by one at the very start. Grab one batch, go through all the layers one by one, and initialize everything, so all the layers, so that they have mean 0 and standard deviation 1. And that's it. That's the concept of LSUV, as far as I can tell. But in the paper, they do something different. They say that, okay, so algorithm 1 is basically the layer by layer setting, grabbing one batch, initializing each layer so that the mean and variance of the weights in that layer are 0 and 1, respectively. That's algorithm 1. But in the paper, they say that algorithm, and algorithm 1 is what they've implemented in Fast.ai, right? But in the paper, they say that algorithm 1 is intended to follow a certain orthonormal initialization procedure. And this is what they say in the paper. We thus extend the orthonormal initialization in Sachs et al. 2014 to an iterative procedure described in algorithm 1. And so I didn't look up this paper, but it says that Sachs et al. That procedure is implemented in 2 steps. First, fill the weights with Gaussian noise with unit variance. That sounds understandable. But the second part is decompose them to orthonormal basis with QR or SVD decomposition and replace the weights with one of the components. That to me isn't sufficient for me to understand what they did. But the point is that there's this pre-processing procedure that involves this orthonormal initialization step that Fast.ai has ignored. And so I asked the question on the forum, why did they ignore it? And did they find out that it wasn't necessary or whatever? So I haven't gotten an answer to that question yet either. All right, moving on. Oh, okay, so now we might as well just go through that, that LSUV procedure. I'm just gonna stop sharing this notebook, the slides, and go to the LSUV notebook. And since my LSUV notebook seems to be broken because I did something weird, I'm gonna go back to the original one, and I'm gonna share that one. There, everybody see that LSUV notebook? Yes, no?
Yep.
Okay, so this is the LSUV, this is the notebook 07A. And so he's basically doing the usual thing here first. He's grabbing the MNIST data, building a CNN, specifying the layers, the number of channels in each layer. Remember the MNIST data is images, but they're only single channel images, and so it's not the usual RGB thing that you might be used to dealing with. So, and here the layers, expand the channels to 8, 16, 32, 64, 64, and then finally the output has 10 channels for the digits, right? So let's just do that. I think we've done this before. This is the preliminary step in a lot of these notebooks, just grabbing the MNIST data set, building a network, and running that. The learner and the runner, and then we fit it. Okay, so, and wait, did that work? Did that run? Let's see. Yeah, so we end up with 95% accuracy after 2 epochs. Now he says, okay, let's recreate the model, and then we'll try again with LSUV. But first, he's going to do something that's going. Oh, okay. Why does he do this differently? He grabs. Oh, he's just grabbing a single batch here. He's writing a function that he's going to export that grabs one batch and using a callback. So now he runs that to get XB and YB. We can look at them. What do we expect XB to look like? We expect it to be, I think the batch size is 512. Let's see. The batch size is 512. The image size is 28 by 28, and there's one channel. So I think we expect 512, 1, 28, 28 to be the batch size. Let's see. Oops. I need this. Yeah, there it is. So the batch size is 512. Remember the 0 index is the samples in the batch. So if you were to pull one of these, you would get a single 28 by 28 image, and that image would be of a digit. So it's a good idea to sometimes, when you do things, to interact with your notebook and just sort of query it. And before you query it, you ask yourself, what am I expecting to see? And then that helps you to verify that things are acting like you think they should. All right, so now he's got this little function that finds that it's kind of a little helper function that finds the modules that we're interested in. Of all the modules, of all of the modules in the model, the only ones we're interested in are the convolutional layers, and for this exercise. So he's building this little helper function, and now we can find all the modules that are linear layers. And so first he builds this list of linear. Oh, it's actually a tuple of sort of blueprints for things that we're interested in, like a conv 1D or it's a conv 2D or a conv 3D. We haven't dealt with all of these things yet. We've dealt with a linear model, and we've dealt with a ReLU. So he's asking, if our model is one of these things, then then return true. If it's not, return false. So now he finds all the modules that are in our model that are one of these things, right? So here's mods, and you can see you've got the convolutional layers that we specified to build this model. But let's just compare to everything, so we can see that some things got excluded. So this is everything in the model. And notice that because the last 3 layers, sorry, yeah, the last 3 layers were not, wait, what is it? It says linear. How come it didn't pick up this layer? I'm a little confused by this because it's looking for the layers that that are one of these things, right? And we notice that we have a conv layer that has a conv 2D in it. They all have conv 2D. These are all 2-dimensional convolutions. And there's 1, 2, 3, 4, 5 of them. And 1, 2, 3, 4, 5. It identified all of those. But there's also a linear layer here at the end. So obviously it ignored the adaptive average pool because it wasn't one of those things, and it ignored the lambda because it wasn't one of those things. But it also ignored the linear. I'm not quite sure why it ignored the linear layer. But anyway, so it basically it picked out all the convolution layers. We can move on from there. We picked out all the convolution layers. That's what mods is. And now he's got this helper function to get the mean and standard deviation of the output of a layer that we leave a hook in. So that's what this append stat is. So now you put the model on CUDA, on the GPU, and then you can use this hooks thing with this append stat function to look at the mean and standard deviation of the weights in each of the convolution layers. So here we go. And notice that the means are far from 0. And they're not 0, which we want the means to be 0. That is, notice we're printing the mean and the standard deviation of the weights in that layer. So the left-hand column is the means, the right-hand column is the standard deviations. And you notice that the means are not near 0 and the standard deviations are not quite 1. So there's something to be desired there. So that's the whole. So then the next thing is we're going to build this LSUV algorithm. And it's all in this cell right here. This is the entire LSUV algorithm that they've implemented in Fast.ai. And all they've done is they've said while there is a batch, while model of the input batch exists, that is, it's not none, and the absolute value of the standard deviation is, that is, the standard deviation minus 1, if it's bigger than 1 times 10 to the minus 3, in other words, if it's farther away from 1, and the standard deviation is farther away from 1 than 1 part in 1,000, then we want to do something about that. And so what we do about that is, I've actually altered the original for a moment. I'll get back to that. I'm going to put it back the way it was. The first thing they do is they subtract the mean from the bias to put the bias closer to get the bias closer to 0. Then they do the same thing for the standard deviation. If the standard deviation, so if the mean is bigger than 10 to the minus 3, then let's do something about it. Let's subtract the mean from it. And then it will be closer to 0, right? If you subtract, if you got a bunch of numbers and their mean isn't 0, and then you take their mean and subtract it from each number, then the mean of those numbers should be 0, right? I don't know if I'm making myself clear. But anyway, they're removing the mean and that effect of that is to make the mean of the new set of numbers to be 0, like we want. And the same thing here. If the standard deviation is farther away from 1, is not close to 1, that's what this says. If the absolute value of standard deviation minus 1 is bigger than 1 part in 1,000, then we take all that data and divide it by the standard. We basically normalize it by the standard deviation, and that new set of data should then have the standard deviation close to 1. So that's the idea here, is that for each layer we're going to do this, we're going to grab a batch, and then for each layer, we're going to force the weights. We're going to actually remove the mean and divide by the standard deviation. And the end point of that process is that we're going to make the mean 0. We're going to try to force the mean to be 0 and force the standard deviation to be 1. So that's what this does. Let's run that. Let's run that, and now we shall. So this is defining the function, and this is actually implementing it. For m in mods, we're going to do this on one batch. And so here you see what happens. And look at those results. We're seeing that although the standard deviation is close to 1, but the mean is not necessarily close to 0. It's better than before, but it's still not close to 0. And that's what Jeremy says. Note that the mean doesn't exactly stay at 0 since we changed the standard deviation after scaling the weight. So this is what they end up with, and they're happy with it because really the mean doesn't matter that much, I guess. The standard deviation is what's the most important, so that the data, so that the weights don't blow up. If the weights are always initialized to have a standard deviation of 1, then they're not going to blow up. We've seen that before. But I found one thing by playing with this, that if you reverse the order, because I was bugged by that why shouldn't the means be close to 0? If you reverse the order and try it again, you now have perfect initialization. I'm still not sure why that works, but it works. In other words, if instead of removing the mean first, you scale by the standard deviation first, then remove the mean, then we get perfect initialization. 10 to the minus 9 is essentially 0, right? The mean. And the standard deviation is pretty much the way it was before, close to 1. So that's just one tweak that one can make. I'm not sure it has any effect down the line. It doesn't really matter, but it just, I don't know, it just made me feel good to see that. Then I looked in the forum, and I found that, and I wrote a post about that, just a brief post, and then I found that Stas Beckman had already discovered that months ago and had already posted about it. So after I wrote my post, I then referred back to his post because he found it before I did. Okay, so finally now you got this done, you run the model.
Joseph, going back to that, in your situation, aren't you first running it so that you kind of make the variance, standard deviations 1, and then you're rerunning on those numbers again to take care of the means, right? So it's not really running one before the other. It's kind of like, does my question make sense? Because you're running it on the same model XB, so your parameters have you started with random parameters, you ran it once, they kind of normalized to like zeros and ones.
Oh, okay, I see what you're saying. Okay, so let's go back and start from the beginning. So we'll go back, we'll build the model again. You're saying I cheated because we already had close to 0. We already had things close to.
No, I'm saying like your strategy would work, but I'm saying like instead of my understanding is not swapping out the order, but running it twice with the order interchanged.
I see. So this time we're not running it twice. We're just running it the first time.
Mm-hmm.
And so here you see it's not working. The means aren't close to 0. The standard deviations aren't close to 1. We now try this with the order. This is the reverse order from what Jeremy had. Do that, and we run this, and it still works. So it's not because we interchanged the order. It's not because we ran it once.
Okay. Cool.
Okay. So now I want to do this, and there. We now have 97% after 2 epochs. Is that better than we had before the first time when we did it without LSUV? Let's see. Here's what we had, 95%. So I suppose we're doing better with the LSUV. I'm not convinced that I'm not convinced that it made a huge difference, but I guess 2% is big. So anyway, that's LSUV. And then you got to save it. All right. So that's the first 4 minutes of the the first 4 minutes of the video. He actually talks about the simplified running batch norm at the very beginning for about 3 minutes, and then he talks about the LSUV for another 4 minutes, and then he starts talking about the API, and that is the data block API. And this is really interesting because he's used data block all along, even in course 1. And so now we're going to see the nuts and bolts of what it's actually doing. So let me see. I'm going to use my version. My version doesn't work, but it has all the comments in it, so I'm going to use that. There was somebody who discovered that their version of Notebook 08 didn't run for some reasons, and he posted about it. And I actually wrote a post about that also. Let me go back to here. I'm going to unshare and then share my, let's see. Well, I wrote a post about this, and I put it on the Slack channel, and I also put it in the forum. It's about how I thought I could get my notebook to run following this prescription that this guy gave. But it didn't seem to, well, it fixed one thing, but it didn't fix another thing, and my notebook didn't actually run. And I believe the reason why my notebook's not running is because it's on Windows 10, and you really need to be on a Unix machine. That's what I think. So going back to my notebook, maybe I'll go back. I'll look at that Slack post first. Sorry to keep pulling you back and forth here. I'm going to go to the Slack post, stop sharing this, and share that Slack post again. So there's the Slack group post. All right, get rid of this. And okay, so this is the guy, Exino7 discovered a couple of corrections, and he posted about it that he needed to make the 08 data block execute without errors. And he outlined these 2 steps, but he didn't really tell exactly what you do. So I thought I would just summarize exactly what you do to take care of this. You have to copy these lines of code because it calls this thing called cosine 1 cycle anneal, which is not defined anywhere. So and it turns out that, again, in the repo, the version of the notebook. Remember how this works in the repo? The Jupyter notebook. At the end of every Jupyter notebook, you save it in the form of a .py file. Remember, and what he found was that the .py file that was saved by 05_anneal.ipynd, the notebook that was saved at the end of that didn't match the notebook that was in the repo. In other words, they used a more advanced version of the notebook, of the Jupyter notebook for 05_anneal to generate the NB_05. Does that make sense? So to fix that, you should not edit the NB_05.py file. You're never supposed to edit those, right? Because those are auto-generated. And remember, they're found in the X folder, in the /exp folder. These files, the NB_blah blah.py, they're files that are generated at the end of each notebook. You then run this script that generates the .py file. Do you remember that? At the end of every Jupyter notebook, there's one line that executes a script that generates these .py files. So since the notebook was missing these lines, the notebook that generated the existing nb05.py file that we have, not the one in the the one in the repo is correct, what I'm saying. But when you run through your notebook 5 at the end, you overwrite the good one that's in the repo, and so you screw it up. So to fix that, you just add these 3 lines into your 05 anneal notebook, which defines this cosine 1 cycle thing, and then when you generate the .py file at the end, then it generates a correct nb_05 py file. Okay, so that's what I'm saying here. At the end, you execute this thing, and you're good. It generates a corrected nb05 file. And the second thing he found was that was a problem with the nb_05b file that was generated from the 05b early stopping notebook. And there was one line missing in that, and I think Prashant knew about it because I guess he has the right version or something. That line that's missing is in the initialization of the runner class when you need to have this this property added. So what you have to do to fix this is to add this line, is to copy this line and paste it into the 05b early stopping notebook as the first line in the init method of the runner class, just before the line that specifies the callback list.
Sorry to interrupt. Are you sharing your screen? I lost.
I'm sorry.
Say about
I'm sorry. Somebody should have. Yeah. Let me. I'm so sorry. I've been blabbering on, and you haven't been following a word because you haven't seen what I'm pointing to. So this is the post that I made in the. Sorry about that. This is the post that I made in the Slack group describing these corrections that have to be made in order to have proper versions of the nb_05.py files and the nb_05b.py files. The fellow, the guy named Exino7 discovered that the versions of these 2 py files, this one and this one, were different in the Git repo, in the Fast.ai Git repo, than the ones that your notebook generates when you run through it. Okay, so we have to fix those things, and there are 2 fixes. One is, one is you have to copy these 3 lines to generate this, to add this cosine 1 cycle anneal function. It's a schedule. You paste it into the 05 anneal notebook under the other schedule functions. And I just made a note that this copied code, how do we know with this? He found that in this notebook nb05_py, the original version in the repo has these 3 lines of code in. So the point is, don't edit the nb05.py file because those are auto-generated files. They're not meant to be edited. Instead, you edit the original notebook that generates that file, and then you generate the file, like this. Does that make sense to everybody? Because if it doesn't, please ask. Unmute yourself, ask a question if you have one. Okay, then I assume everyone is good with this. Okay, and then the second fix is to add, is to go into the 05b early stopping notebook, and under the init method of the runner class, you can find that in that notebook, you copy in this line as the first line in the init method. Okay, it goes right above this. The existing first line in the init method of the runner class is this, and so all you have to do is paste this line above this line. Okay, then you save it. Then you execute that last cell in the notebook. Remember, the last cell is always it always does this. It executes this notebook to script, and it generates the NB NB_05b.py file from directly from the Jupyter notebook. Okay. Once you've done these things, you now have everything that you need to be able to run it. There's one step I left out of here, and that is that remember, every successive notebook imports the notebooks before it. So now that you've got corrected NB05B files and NB05.py files, you need to import them by executing the last line in notebook 6, and then that'll import everything up to notebook. That will import everything up to notebook 6. And then in notebook 7, you have to execute the last line in that one again, and the last line in notebook 8. And the last line in notebook 7b. Because remember, these things work serially. Each notebook has to be executed in order before the next one can work. So what I'm saying is that now that we've corrected 5 and 5b, you now have to go into 5. Now everything is fine up to 5b, but you have to serially execute the next notebooks in the series, that is notebook 6, notebook 7, and notebook 7a. And once you've executed those notebooks, you don't really have to execute the whole notebooks, you just have to execute the last line in them. Then when you import, remember the first line in data block in 08 is importing the .py file from notebook 7b, and everything will be all right if you do that. Does that make sense to everybody? Let me show you what I mean. Go back, I'm gonna unshare, go back to the 08 notebook and share that right here. Now, everybody seeing the 08 Data Block API Foundations notebook? Yes? No? Hello?
Yes, we see the data foundations.
Thank you. Okay, so what I'm saying is that you have to create all of these. Okay, you've already created the proper versions of this and this. Then there's let's see, at the beginning of notebook 6, you have to set num threads to, and you export. So this is what you do at the top of notebook 6. You import notebook 5b, which we just fixed, right? You have to do that. And then at the top of notebook, okay, and then you save notebook 6. And then at the notebook 7, you import this. At the top of notebook 7, you import notebook 6, which is now corrected because you've executed, you've executed the IPyNB notebook corresponding. Then you execute the notebook 7. In other words, you have to serially generate each of these .py files so that they'll incorporate the changes of the ones before them. Does that make sense? Okay, and once you've done all that, then the last file will then have all of the current things in it. That is will have all of the current functions available in it, this notebook 7a. So normally you would just import this one. That's what the first line used to be. But what I did was I also exported all of the previous ones to incorporate all of those changes that we just made. That's the last thing that I didn't say in that Slack post.
I'm not sure, Joseph, is that required?
Yeah.
Because once you write your 05 notebook, you're basically updating exp.nb05.
Yes.
And then when you import exp.nb07a, that automatically gets the updated one, right?
That's what I didn't think was the case. I thought that
I haven't tried it out, but I think that should work. I don't know if someone else has tried it out, but I'm not sure.
Yeah. So if you think about it, Notebook 7A was saved before you made the changes to Notebook 5, right? So it couldn't know about the changes that you made in Notebook 5 and 5B, right?
No, but then when you're rerunning that cell, when you're importing Notebook 7A from EXP, that should know, right? That is just going to read what NB6 is or what NB5 is, and that you have already updated because you did the notebook to script conversion.
Oh, I see what you're saying. So you think that if the Notebook 7, even the old version of Notebook 7, if you run it, it will automatically go and
right.
it will get all the notebooks behind it. Okay,
yes.
That might be true. So then we don't need these. Then we wouldn't need these lines. Okay, somebody can try that and see if it still works. But anyway, so let's now, having done that, we can now, at least that part of of that problem with Notebook 8 would be fixed. Okay, but there are other problems that I have because I'm running Windows, which we'll see. But
the other issue that I found is the /notebook to script doesn't work or didn't work for me. So I had to revert to what he used to do before, which is Python notebook to script. That seemed to work. So
that's yes.
You know, I don't know why he keeps changing how he saves it, but
that's a great point, Srinivas. I found the same thing. I had to and I think it was in Notebook 6 that he introduced this new way of saving the notebooks where you don't have to explicitly give the notebook name that you want to save. And yeah, I found it didn't work for me either. So I went back to using the shell command that he gave, which is, ! notebook to script, blah, blah, blah. Exactly what you said. I had to do that too. So let's see if we can see how that, and I think he even, let's see. So at the end of this file, this is the old way.
right, that works.
Yeah.
And in fact, even the bang /notebook to script didn't work for me.
Yeah. Yeah. So that's exactly right. I had to do the same thing, and I didn't mention it though. But you're right. Okay. So let's see if we can go through this. Let's see how far we can get in this. I know we're not going to get all the way through it. So I kind of just went through here and organized in my mind what it was. I didn't do too much except for put in a bunch of comments. So I just organized it in sections. First, the section 1 is just to the image item list, create this image item list class. Okay, we'll go through that, but I just want to give an overview now. The second section is once we've done that, we can now prepare for modeling. And Jeremy has this outline of basically, this is what I really like to see in documentation. He said this is what his thinking was when he wrote all the code below. So he made a list of subtasks and get files, convert raw PIL images to RGB images, split the validation set by some random percentage, blah, 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 label the images from the folder names. Then he does transforms on each image. Then you have to transform the images to tensors so that you can handle them with PyTorch. Then you build a data loader. You have to run transforms on the batch that are optional, but we'll look at them again. Then you build this data bunch class, and then you add a test set. He doesn't go through that, but so these are all the steps that he does. And so you can now just see, he just goes through and accomplishes each one of those little subtasks. And that's that. Transform to tensor, prepare the image data from labeling. And then finally, the third section is now you can just see how to use this data bunch in a model. The last section is pretty short. it's basically showing off all this new functionality that he built in, and there it is. And then at the end, you export it. So let's just go through some of this. Get the data set, the ImageNet. And he built this new, there's some part of the lecture where he talks about this new data set that he built called ImageNet, which is a small data set. It's a 1% of the size of the famous ImageNet data set. And Jeremy's idea was, instead of wasting all this time training a data set with 1 million images, that takes a lot of processor time and a lot of turnaround time to see how your models work. He said, let's train our models on a much smaller version of it, which seems to me to be a great idea, because your training time is way cut down and you can make your iterations and improvements and so on without having to wait a long time for your models to run. So he built this mini data set called ImageNet, and he actually makes it on, serves it from the AWS system. And so there's this, you can now just download it. Then you have to use this computer vision library called Pillow, which in order to, which he, let's see, what did we do? Where did we get that? I think Pillow is already installed in PyTorch for us. So this first step isn't using the Pillow library, it's just untarring things. This is where you, so I was wrong. This is where you actually get the Pillow library. Let's see. All this is doing is setting the path to point to where the directory, where the images are stored. And the interesting thing is, at least on my machine, is that they're stored in this directory under my user directory, which is just .fast.ai, the name of that directory. And under .fast.ai, they put in this data directory, and that data directory has subdirectories with the data for various projects that we're doing in this class. So it's kind of interesting to know where that data is coming from. Anyway, so here's where he imports the Pillow library, and he imports OS, which we'll see why in a minute, and MIME types. And then he adds this thing on the fly, this method to the path class. He just shows how you can add this convenient method that lets you list all the directories in a path. So now, if you do that for our top directory, ImageNet 160, you see that it doesn't list all the subdirectories, it just lists the level under, the level beneath the top directory. So we see that in that ImageNet directory, we have a train and a validation directory. And then if we look what's in the train directory, we have one folder for each of the types of images. So what Jeremy did, I think there were 1,000 classes in the original ImageNet directory, and Jeremy picked 10 of them. I don't remember what they are offhand, but he picked 10 classes and only took the training images from the ImageNet directory that were in those 10 classes. So here we have the training examples are organized by their category. So I don't know if these are all, I don't know, they could be all dogs or they could be all snakes or whatever. Each folder has a different class of images in it. And the validation images are organized the same way, and you see that they're the same classes, the same 10 classes. Okay, so he simplified the problem. We're not dealing with a situation where your validation data could have different classes in it than your training data. That's a whole big problem in itself, but we don't have to deal with that because we've created this easy data set where everything is hunky-dory and nice. Okay, so now we list subdirectories and we already did that. Look inside one of them. So he builds a path to the first class right there. And then we can look at the first file in that in that folder. Okay, we look at the first file name. So we're just looking at what this ls does is it lists all the files, but there are probably thousands of them in that subdirectory. So instead of looking at all, at the huge number of files, we're just going to pick the first one. So the first file name that we come across is this one, and then he displays it using the pillow library. So we open up that image and look at it using pillow, and then we use imshow, to see the image again. And imshow is nice, is more informative than just opening the image with pillow. It's actually showing us the coordinates. In other words, this is the pixel coordinates. And the standard way that these images are mapped is that the origin is at the top left, which is kind of different than we're used to thinking about, but it's fine. So the row number goes down this way, and the column number goes across this way. All right, so now this is actually cheating. He told us from the beginning we're not supposed to use NumPy, but he's doing it here, but that's okay. I don't even understand why he made that restriction in the first place. So he's importing NumPy. Oh, he's converting the image to an array using NumPy. So that's what we did there. And there it is. So the original images, you can see they're 160 by 213, I guess. So that's the dimensions of the image. And then there's three, because it's an RGB image, there's three channels. So the shape of the image is that way. And then later on, he mentions that Python does things backwards. Its syntax for discussing images like this is to put the channels first. And so you have a problem when you want to go into PyTorch, you have to switch. You basically have to reorganize this array to permute the indices so that the channels come first. And he writes a little helper function to do that, and another helper function to put it back into regular pill format. Okay, so now he's just looking at, so IMGA is just an array, is a NumPy array, and you can look at, actually look at some of the values of the pixels, and you see that there are numbers, and in keeping with the image format, the numbers in the pixels, the pixel values are numbers between 0 and 255, where 0 is completely black and 255 is completely white. So that's just looking at what the images looks like. Okay, then he builds this little function that that generates all the possible image extensions that you can have. And that's what this MIME types thing that he imported was, that MIME types has records of all the different kinds of image formats. So he builds this little tuple of all of the image formats, and then he makes it into a list. That's all he's doing here. So he makes a list, and it's all in one. This is kind of strange. Oh, he's joining each element by this 2 spaces. So he makes a single string. That's a string command. That's a string method. So he's building from this list of extensions, he's building a single string that just has all the extensions in it. And then he has another function called setify. And if the input is already a set, then that's fine. If otherwise, you listify it and then you make it into a set. So that's what he's going to do here. And now this is interesting. Jeremy has this methodology that he follows. When he creates a new function, he sometimes writes a series of tests to make sure it's working the way he wants it to work. So here's some of the tests that he ran. Suppose you give it, let's see, you give it these 2 things. A string wait, what is this? Setify of AA? Yeah, setify of a string, you expect to see a set that has that element in it because there's only a single element. And when you run this and nothing happens, that means it passed the test, because that's this test eq, means that if these things are equal, then don't do anything, otherwise complain. So another experiment, AA and 1, a list with AA and 1 gets turned into a set with AA and 1, and that worked. The empty set, a list with nothing in it, gets turned into the empty set. That worked. Setify 1, and that gives you a set with 1 in it, with 1 element in it. Setify the set containing 1, it doesn't do anything. It just returns the same thing. And we can add another test. What if we had, what if we gave it 3 things? We would expect, I'm sorry, let me undo that. That's the way it was. We can add another test just to convince ourselves that it's really working. What if we give it a list that has redundant elements in it? So what if I say AA, B, AA? I've given it a list that has redundant elements in it. And what do I expect to come out of that? I expect the set is only going to have the unique elements in it, because that's what what set does is it looks for all the unique elements and only keeps those and puts them in a set. So I'm expecting that my test should satisfy this. In other words, if I run this, I should get no complaint. And it works. Does that make sense to you? Another test. Okay. Okay, so now he's got this underscore get files, which is going to return the full path names of all the files in the folder P that's passed to it. If there's no extensions, in other words, so you specify this list, there's a keyword variable, you can specify a dictionary of extensions, but if you don't, then this underscores get files command is going to return the full path names of all the files in the folder that's right under it. But if you specify a list of extensions, it's only going to return those file names that have extensions from that list. So it's a cool way. So what he's doing is he's inventing a way to look for all the images in the subdirectory. We don't care about anything else. We just want the images. So that's what he's doing. And when I looked at this function, I was wondering, why do you have to make P into a path object? And the answer I found in the next line is that path objects, actually in the next line right here, path objects have pretty interesting properties because you can do this, and it interprets that slash not as a division, which would throw an error, but it interprets the slash as a subfolder, as an indicator of a subfolder. So here he's the result has a list comprehension that generates a result that is a list of all the full path names of all the files in that folder at one level beneath that folder. All the file names if there's no extensions specified, but if there's a list of extensions specified, then you only want the ones that have a suffix that matches one of the extensions. Does that make sense? So, and the extensions, of course, is the list of these, okay, of these image extensions. So he's looking for all possible image formats in here. That's what this little function does. So now he uses it, and okay, get files. Given a path, he generates a path name, a list of let's see. So what do I do here? So he generates this list of file names, and he uses this thing called scandir, which he spends a little time in the lecture explaining that Scandir is wickedly fast. It's a really great way to look at subdirectories. It's a very fast way to get the files, to get the file names in a subdirectory. So he recommends the use of this command os.scandir. So he does this. He uses Scandir. He generates a path. Remember the tench fish, whatever. All the files in that path. We could, let's see. There are 50 file names, it turns out, because I ask it to print the length. So instead of printing all 50 of them, we just print the first three, or the first three. So there they are. That file, and that. These are just images of tenches, right? And then the next one, he says, let's now replace T with the full path names of all the images that have the. So he's going to use this get files command. And so instead of just the names of the files, we have the full path to each of them, right? That's all that is. All right. So now he builds this thing, which is a little bit more sophisticated. You want to find all the files in all the directory tree. So there could be subdirectories and stuff, right? In a general case, there might be subdirectories that have images in them, and you want to. So he's building this utility function that finds all the files with the specified extension in the entire directory tree. And to do that, he uses this another command that he's very excited about called os.walk. Because this command is also a very fast way to look at to examine a directory tree. What happens is if you give it a path, it will return the path, the folder names and the file names of every single subdirectory, of every single subfolder in the tree. Okay, and so now he has this sort of a souped up version of get files that not only looks in the directory below the given path, but it looks in all the directories below that. So that's what this thing is. And now he uses the get files. It's doing the same thing here as the underscore get files, but in a more general situation where there was a huge directory structure, a huge directory tree structure, it would root out all of the image files. So he built this more general function and he exported it for later use. Okay. Now you can use this get files to start at the top level. And so now for this command, you actually need the recursion because you're starting in the top level. That is, we're starting here. So it finds, it goes into all the subdirectories and finds the images. It's the same images, but now it found them starting from the top directory instead of starting with instead of starting in the ImageNet 60 directory. Sorry, instead of starting in the in this directory. All right. So he did that. All functions equals get files because equals true. So okay, so this is the same command. This is just looking at the first three of them. Now he's going to collect all the file names in the entire ImageNet directory, and there are 13,394 of them, and they're now in this list. Okay, so now he wants to show how fast this is. The reason why he said it's because ultimately we're going to operate on ImageNet and not just ImageNet, and so we're going to need something really fast because it has millions. It has 1 million images in it. So he does this timing, and I'm running over. So anybody that needs to leave, sorry, you probably already left. But if you want to stay, I'll stay. I'll just try to get through some of this. Okay, so let's run it. And oh, funny. Last night when I ran this, I got 211 milliseconds, and I was complaining because Jeremy gets 73 milliseconds. All of a sudden, my computer got faster. I'm not sure why. So anyway, it's fast. It's a tenth. That's a tenth of a second to read whatever that is, 13,000 files. So that's pretty fast. Okay, the next section, we basically build all the pieces. I think section 2, we build all the pieces of all the other pieces of data bunch of the data bunch. Well, up to the last part. So what if we go through? If we go through the rest of section 2, what do you think about that? Or should we stop now and leave this till next time? What do you think?
I think stop now. Okay.
I mean, I'm fine if we stop now and just resume. We can resume next time.
That can we, like, is everyone ready to start like 15 minutes earlier next time?
Yeah, that's right. Prashant has an idea that we should start at 8:30 from now on, and then we won't run over so much.
Yeah.
Are people okay with that?
Yeah.
Okay, I'll make a note on the. I wish I would have asked that before because everybody's left now. But I'll make a note on the Slack group, and the next announcements will have the 8:30 starting time. Okay. So I'm going to stop here and take up here next week. Does anybody have any? So next week we'll try to finish this and also start. We won't be able to finish the optimization notebook, but we'll start it. Anybody have any questions before we call it quits?
Just to answer the batch norm question that you were asking previously, do you mind pulling up that notebook or that post where you had your questions?
Yes. Batch norm. Batch norm. There it is.
Yeah, I had some. I understood it a particular way, so I just wanted to see what you guys think about the. Where is the MOM one calculated?
Yeah. Question. There it is.
Okay, cool. So if you kind of look at that, the way I was looking at it is, so self.mom is 0.1, right, by default.
Yes,
Let's, for the timing, drop out math.square root bs minus 1.
Yeah.
So then you basically end up getting 1 minus 1 minus 0.1. So mom 1 is basically 0.1 then. All right.
1 minus, okay, 1 minus, yeah, it's mom 1 is the same as mom if you do it.
Exactly.
If you omit that, yes.
Right. So now the other thing we remember with lerp is that the idea is when you're using momentum is you weight your current your current sample or whatever the current thing is much smaller. Like it'll be 0.1 versus the older stuff that you've been calculating is higher, which is 0.9 in this case.
Yes.
And now if you bring back that square root of BS in, basically the understanding is that as BS increases, that is your batch size becomes bigger and bigger, your current batch is much more trustworthy, so you can weight that higher. So that's what you also calculated, right? Like as your BS becomes more, mom1 becomes more, which basically means your current sample can be weighed more. And that's the way I kind of understood that.
I see. Okay, that makes sense. Prashant, that's excellent. So, I mean, we saw the trend is that the bigger the batch size, the bigger is mom1, and they're bigger. Therefore, the bigger your current batch gets weighted, because that's what you said. Is you're referring to the lerp command.
Right.
And in this notebook, I looked that up for us because I just basically copied some stuff from PyTorch docs so that people could see what lerp is. And as you're saying, this is what lerp does. Is it takes the starting value and then it adds the weight, a weight. This is actually the linear interpolation formula.
Right.
But it actually is also an affine transform, because if you let me just do this, insert cell below. So let's call out one. I want to make some simplified names. I'm going to put O, S, and E. So O equals S plus W times E minus S. So this is the output. Given a starting value and an ending value, it gives you this interpolated value. And the weight W is intended to be how far are you, what's the fraction, in other words, the interpolation point is what fraction of the way between S and E. That's what W is in linear interpolation. W is actually intended to be, let's see, is the fraction of the way between.
I don't know if it helps, but the way, at least, it helps me kind of look at that formula as if you rearrange that as.
That's exactly what I'm doing.
Right, okay.
You're thinking exactly what I'm doing. So if you take S and group the S's together, it's S times 1 minus W. This is the formula that that Prashant is referring to, plus W times E. Sorry, times E. So So this is what you said, right? Prashant, you're rearranging the formula, and this is an affine transform when weight is between 0 and 1. Then this is an affine. It's called an affine transformation, which is neither here nor there. But the point is that it gives so S would be the original, the value up till now. I should rearrange it this way. So, okay. So now this shows clearly we're 1 minus W is the weight applied to the previous measurement, and W is the weight applied to the current measurement, right? And so what we have is, in our case, is going to be the W is what we're calling mom1, right? Or mom, whatever.
Mom1, yeah.
Momentum plus S times 1 minus mom. So yeah. So what you're saying is that it's weighting one, since mom is given as 0.1, is usually taken as a default value as 0.1. It's weighting the previous result by 0.9 and mixing that with 0.1 weighted of the current result. So it's putting heavier emphasis on what went before. It's preserving a memory of what went before, and it's not allowing the current state to change the result that much. So it's being very conservative, right? But what you're saying is that as the batch size increases, now you're effectively decreasing this number and putting more weight on, that is, back up to here where you're dividing by the square root of, there it is, dividing by the square root of batch size. You're putting more emphasis, more weight on the current measurement. You're putting, so initially you're putting more weight on the previous measurement. You're being very conservative, and you're not letting the current measurement weigh in that much.
Right.
But as the batch size gets bigger, you're trusting your current measurement more, and you're allowing it to influence the final result more. That's what you're saying. That's a really good insight. Thank you.
Yep.
Great insight. That helps to, that basically answers my question. I just don't know how they came up with this. Or it would be great if they would have just given that simple explanation that you did, Prashant. Anyway, that cracks that open for me, and I think the rest of it was my question about this ridiculously convoluted thing that they have called debiased. I crossed out some of these because I saw I started trying to recreate the simplified batch norm from their notebook that I saw just from the screen views of it in the lecture, but then I gave up on it because I figured there's probably an easier way to get hold of it. But anyway, the point is that they had this whole convoluted thing about debiasing, and they found out that it's really unnecessary. So they eliminated it from the newer version. The simplified version is much easier. It doesn't have that problem. So my only problem now is
I believe we still need debiasing, not in this case, because the stuff that you have commented out here is that basically you end up doing self.debag when you've written means is equal to sums by C, right?
yes, and it actually cancels itself out.
So in
But
this
it actually doesn't. It actually doesn't cancel itself out because he's only doing it if, let's see, he has this. Sorry, let me go back to the original one because I've messed up this one. There it is. It's funny. It's so compact when you don't have comments. So here's the debiasing part. And so in the new one, he moves most of this stuff into here. But see, you're only screwing up, you're only doing nothing if the step in the first 100 batches, right? Because you're not always doing this normalization, you're only doing it for the first 100 batches. So for the first 100 batches, it's doing nothing. Oh, that's right. Then that's the only time you use it. So yeah, it is. It's basically doing nothing.
Right.
Because, yeah. So they eliminated it in the simplified batch run, right? They don't have a debiasing step.
Right. That's not there.
Yeah. So that means that with your explanation of how momentum, why the MOM1 formula looks like it looks, now I understand everything I need to understand about this. So thank you for that.
Sure.
Do you want to post that on the forum? If you look for my question, and then you could post your answer.
Yeah, sure. Okay.
Because that's what Jeremy asked us to do, to look into it, and he said other people should look into it too, so that the whole community can learn from it.
Sounds good. Yeah,
So
do that.
I would love that. That's great. Thank you, Prashant. Excellent. Okay. Any other questions? All right, guys. Thanks for hanging with me for an hour and a half. So next week we'll start at 8:30, and I'll put that on the Slack group and also on the and also on the announcement.